I don't even do. Like if you don't have constraints, I need so much to throw in. I would never play.
All right, guys. Whew, so we were talking about non-homogeneous second order differential equations, and we only had time to do just one because I wanted to give you guys plenty of time to do the second part of the test yesterday or Monday or Wednesday. So the first example we had was second order equation with a polynomial input for forcing function. And this was, again, no different than the first order case. You just propose the same degree polynomial and you got A0 and A1s and you find the A1s, A0, and then you tack on the homogeneous solution, which requires a little bit more work than first order because you have to do the characteristic equation. Now, this is also a first order or first degree polynomial on the right-hand side. So you might propose this, again, a general first degree polynomial like A0 plus A1t, just like we had in the first one right here. But somehow this one, we had no issues in finding A1 and A0, but this one, assuming A0 and A1s are constants, when you plug it into the left-hand side, you'll get 0 plus A1 because the second derivative of this would just make it 0. And then the first derivative would just be A1. And you get an issue where it appears that A1 is not a constant. So it's like a contradiction from your original assumption. And so let's say you said, okay, well, fine, I'll just use A1 as t. And we have no idea what A0 is. So we'll just say A0 is whatever. And then you put A1 as t, and then it'd be t squared. But if you plug this in, the first derivative would be 2t, and then the derivative of 2t is 2, so it'd be 2 plus 2t on the left-hand side, which will not resemble the right-hand side. And so this is an issue where you don't have a solution that doesn't give you a true statement. So there was already a problem because it contradicts your assumption that A0 and A1 were constants. I mean, if you didn't make that assumption, then you wouldn't have gotten 0 plus A1 on the left-hand side. So you're already feeling like unsure about this because it's contradicting an assumption you're making when you first plug it in, but it doesn't even work. So for this one, you might look at it and be like, okay, what was the issue? We want to get this left-hand side to like resemble the right-hand side. And anytime you take a derivative, you reduce for a polynomial, right? So if you have a polynomial and you take a derivative, you always reduce the degree, right? So each time you take a derivative of a polynomial, it goes down from like t squared to t to constant, or t cubed to t squared to t to constant, right? So the issue was A0 plus A1t, that's like it has only up to a t term. And so when you took all these derivatives, it just reduced it down to a point where on the left-hand side, there were no more t's left. So like just intuitively, what do you think your proposed particular solution form must contain in order for, after all these successive derivatives, you still retain a t? In other words, was this enough t? Like what do you intuitively expect that the proposed solution form might need? Yeah, it might need to be increased by at least another degree or maybe more, but like you definitely, if you can get like a higher degree polynomial as your proposed solution form, then all these derivatives that you successfully take will potentially preserve at least a t that will resemble the right-hand side. So using that intuition, what I'm going to do, which is not going to be initially, I'm not going to justify this initially, but I'm just going to say, using that intuition, why don't we say that our proposed solution form, I'm just going to say, should be this original one that we had, but I'm going to take the whole thing and just increase the degree by multiplying by t. So I'm just going to take that whole solution form that we had initially, but introduce an extra factor of t to the whole thing and multiply that. And that will, of course, increase the solution form by an extra factor of t. I mean, if you multiply this out, you will get your t squared term. You'll get this will just be a naught t plus a1 t squared if you just distribute the t. Let's try this one. If you try this one and plug it in, then you'll have a second derivative that is going to require, well, let's just compute the derivatives like on the side here so that like we can just, so this is your xp, then what's your xp prime? Xp prime would just be a naught. And then this one would be 2a1t, right? And then xp2, xp double prime. The a naught's a constant, so that goes away. And you just have 2a1. I'm just doing this on the side because, you know, it's just a little, because I'm going to plug it into x double prime, and you need to take prime first. So this is just going to be 2a1. That's the x double prime term. Plus your x prime term is going to be this thing. So I'll just, and that is it on the left, and this has to equal t. And then you will try to match terms. So you'll say that there's a t term here, and there's a t term here. So this automatically gives us that if you have 2a1 has to equal, right, I'll just write it, 2a1 has to equal 1. Therefore, your a1 has to equal half. That's that one. And then you also have that these two terms, which are constant terms, have to vanish. So that just means 2a1 plus a naught has to equal 0. But you also know that this a1, I'll just do this and say the half can get plugged into this a1. And so you're left with half times 2 is just 1. Let's say naught is equal to 0. Therefore, your a naught is equal to -1. And so you found successfully both your a1s and a naughts. Unlike when we had the original, we just got a statement that gave us that a1's not a constant. And then even if you and there was no way to find a naught, so maybe you just kept that random or arbitrary, but that still would not satisfy. Here we don't have an issue where we get like a contradiction where we assume that a naught and a1 are constants, and we indeed get constants for a1 and a naught successfully. And I mean, I'm not going to go through the trouble of this, but if you did plug this, so what's the solution that we get when you do this? This just means that this is our new solution form. So you're going to plug in a1 and a naught into this right here. So this a naught will be equal to 1 and -1. And then this a1 will equal to half. And so you'll get your particular solution is just going to be equal to -t plus half half, not a t squared, half t squared. And this, unlike this weird thing, will, if you plug it into the differential equation, satisfy the differential equation. So it's going to work. And then, of course, your general solution is going to be a little more work. So I have to actually write the characteristic equation for this. So if you have x squared plus, or x double prime plus x prime, that's going to be r squared plus r equals 0. So this is just defined x sub h, which is homogeneous solution. You'll get the r's factor. So you'll have r plus 1 is equal to 0. So therefore your r will equal 0 and -1. So I'll just move this over. Therefore, your homogeneous solution will equal C1 e to the 0t, which is just going to be 0. And then you're going to have plus C2 e to the -t. And then e to the 0 is just 1. So this is just going to be C1 plus C2 e to the -t. This is your homogeneous solution. it's a distinct real roots. So you just have one solution is C1 times e to the r, one of the r's, and then C2 times e to the other r. But one of them 0, so it's just c to the e to the 0 times t, which is still e to the 0. And that reduces to this. So when you actually write the full general solution, it's going to be built off of the particular solution plus the homogeneous solution. So this purple one right here was our particular solution. And then you're adding to it your homogeneous solution. And of course, I can say that these two are, so if you take this, this is your particular solution, and this is your homogeneous solution. And that's the general solution. Again, a second order equation will always have the general solution will always have two arbitrary constants, C1 and C2, and that's just coming from the characteristic equation. That's just coming from the homogeneous solution, which is found by solving the characteristic equation. And then the particular solution in this case was this is the correct solution form for the particular solution. Unlike the initial version, but to fix this one that caused a problem, we had to multiply the original form, particular solution form, by t. And the intuition was then we can get it to have a t squared term so that every time we take a derivative, it reduces the polynomial, but we'll still have a t that remains in order to get it to resemble like the t that we see on the right-hand side. So this multiplying by t thing made sense from that intuitive standpoint. But I guess you could have also just added a2t squared if you wanted to. That's another way to increase the polynomial degree. But then you'll have a0, a1, and a2. And so there's 3 unknown coefficients. So, maybe this was easier because it was just a0 and a1, and it still did the trick, right? It still didn't cause us problems. Yes.
That's what I was.
Yeah. So it's not uncommon for people to say, could we have just added an a2t squared term? Yeah, that would have worked too, because it's basically just adding like another constant term out here, which you would expect, given the work we had here, that additional coefficient would have just been 0. And you could check that on your own. But it's still, either way, the intuition was that these successive derivatives caused all the t's to disappear, and we need at least one left over. You could even add an a3t cubed term or a 4t to the 4th term, but those coefficients would go to 0 because those are going to introduce higher degree t terms on the left with coefficients that are going to have to get those to vanish because there's nothing higher than t on the right hand side. Let's see. I mean, I guess okay, there's another comment I want to make. So if you look at, so you might wonder, like, can I preemptively tell ahead of time if my original solution form needs to be modified? So in this case, we had to multiply by t to get it up. But like, could we have you could always plug it in and notice there's a problem and then be like, okay, it looks like this solution form that I have initially isn't going to work and I got to do something to it. But this one, all of these, you can kind of see if something bad is going to happen. If you ever notice that there is a term in the solution, so like this is under the red, I'll just delete this. If you notice, there is a term in here, this a0, capital A0 term. And then you compute the homogeneous solution. The homogeneous solution has 2 terms, and then one of them is a C1. And in a way, this is like matching with so there's a term in the particular solution that matches with the term in the homogeneous solution. And I'll make a more, maybe this wasn't maybe I should have come back and said this later. But it turns out that there is always a pattern where if you have some term in your homogeneous solution that matches with your particular solution, then there's going to be issues that arise. And so you could sort of preemptively say, this one's not going to have, it's not going to work. So I'll do one that's more obvious. So we'll just say that and move on. But of course, yeah, this one we have some confidence that multiplying by t should do it, and then it worked out when we did that. So this is just me describing this. This is not, yeah, this is fine. So let's look at another case, but this is the second case where you have an exponential. So this is an exponential input. Exponential forcing. This is like if you had a first order, what would you have done? You would have guessed that the solution form is capital A e to the negative 2t. You always look at the right-hand side and try to create one that looks like it. So let's just do that. So your particular solution form, just like we know from first order equation, is capital A e to negative 2t. Then you plug this in. And you end up getting, you got to just take successive derivatives of this. So I'll just do it on the side. So I'll just say x prime of t is negative 2 a e to the negative 2t. It's the chain rule. Xp double prime is the negative 2 comes out and multiplies. So it'll be 4a e to the negative 2t. And then this is my double prime term minus, so it's a minus of a minus, or no, actually it's just x here. So I'll just do minus this one. So it skips the x prime term. And then this is supposed to equal 6 e to the negative 2t. Okay, and then, with these exponentials, you just like divide everything by e to the negative 2t or multiply by e to the positive 2t. So all these would just go away if you just divide all the terms by that. So you're left with 4a minus a is equal to 6, which is the same as 3a is equal to 6, which is like saying that a is equal to 2. So that's it. It's like just a second order equation, but everything about it was the same as if it was a first order equation. You propose the right-hand side is the same form as the e that you see on the right-hand side. That's the only way you can have hope of making all that. Well, that's the only way you can ensure that every term on the left is gonna have an e to the negative 2t term. And then the rule of the name of the game is to find the capital A that will cause all the coefficients that you have like this on the left-hand side to add up to 6, but you're forcing that by plugging in. And so you got your particular solution is just going to be the 2 times A is 2, so it'll be this. So this is like saying this just becomes this after you plug this in, and then you just have to tack on the homogeneous solution. So the homogeneous solution for this is going to be r squared. And the minus x would become a what term in the characteristic? Is the minus 1. It's not minus r because it skips the x prime term. So this is equal to 0. And then you just say this factors to, well, or you should just say this equals just this because you move the 1 across. And so clearly r is plus or minus 1. So your homogeneous solution is going to equal C1 e to the just t plus C2 e to the negative t. And then you would just write your general solution. Is going to be your particular solution plus your homogeneous solution. And that's it. Nothing different from what you did with first order equations. The only thing that's new is the homogeneous solution is more work because you have to do this whole characteristic polynomial thing. And you're plugging it into the original, when you come up with your particular solution form and you plug it into the differential equation, there's a little more work because you have to take a second derivative because when you plug it into x double prime, it's a second derivative. So it's an extra derivative you're taking, and then there's more work for the homogeneous, but nothing was different about this one. Now, what I do like to do with these problems is I like to just like do a slight modification to it. So if you notice, x double prime minus x, x double prime minus x. So I kept the left-hand side the same, but I experimented with like, let's take the right-hand side and change it from this e to the negative 2t is there to one that's e to the negative t, not e to the negative 2t. So that's a slight modification I made here. And then see what kind of consequences that gives us. So if you look at this one, let's I mean, obviously there's like a answer right in front of you, but like let's just, so there's a t e to the negative t that I'm claiming here, but let's not look at that for a second and just said, well, I did change the right hand side to e to the negative t, so from what I know in the past, it's always been, I just take this and then say the particular solution form be e to the negative t. This is what we are used to seeing, right? So this extra factor of t, let's not worry about that. And let's just say we were used to seeing this. But there's going to be a problem with this, and that's why I have this written here. Let's try this and see what happens. So you plug it in. The process of plugging it in requires us to take successive derivatives of this thing. So I'll just write it down on the side here. So xp prime, the derivative is negative, capital A e to the negative t. Xp double prime is going to do the chain rule. So it's going to just essentially give us back the original xp again. And so you'll plug this into the left-hand side is just going to give us this. And then it's a minus of the original xp, which is this, which is the same thing actually. And so you'll get this has to somehow equal e to the negative t. But if you look at the left-hand side, those are two things that subtract from each other. So we're going to get a false statement. We're going to get 0 is equal to e to the negative t. So this is an issue because this is a false statement. And so we can say that this is actually giving us issues. So we can't have this solution form. So the polynomial case, we kind of intuitively expected that, what did we see? We saw that basically this one's just not enough. We need to multiply by t because then that's going to give us like something on the left-hand side that will be, after taking all these derivatives, leaves an extra, at least a factor of t that will show up on the right hand, that's in the right hand side. That kind of intuition you may not have for this one. So for this one, it's like, okay, multiplying by t happens to be the solution for this as well, but I don't know if it's easy to see like that would have been the right thing to do for this case. But it turns out that you want to multiply this by t. And so if you multiply by t, your particular solution form is going to be the original one you had, but with an extra factor of t, so it's going to be e and negative t. And so there's an extra factor of t here. And then you end up, doing the derivative and everything. So the what's painful about this one is that when you have an extra factor of t, you have to do the product rule. So you're going to end up getting, like I usually take the a out and then say I take the derivative of the first term, which is the t term. So it's going to be just 1 times e to the negative t. And then add it with, take the derivative of, well, you just copy the first and take the derivative of the second, but the second is negative. So it's going to be this. And then if you take the derivative of this to get the second term, you'll have to do the product rule on this term right here. So it's going to be a, you got to take the derivative of this to be negative e to the negative t. And then you're going to have to, I guess I'll do this and say square bracket, and then just say, I got to take the chain rule of this. So the product rule of this. So it's going to be derivative of t is 1, copy the second. And then copy the first times the derivative of the second, but the second is going to give you a negative. So it's going to be this. And this is all in square brackets. So what is this? This is going to be like a, there's a minus e to the negative t, minus e to the negative t. So there's going to be minus 2 e to the negative t. This and this will become positive. So I'll write that first and say e to the negative t. And then a minus 2 e to the negative t. So that's the simplified version of the second derivative. This is like just calculus, so everybody can do this. So now that we have this, we plug it into the original differential equation, which is this x double prime thing. So I got to put the second derivative into the x double prime. So this is right here. So you plug in. Minus the original solution form, which is this purple thing right here. Has to equal e to the negative t. And I'm just going to multiply everything out. So on the left-hand side, it's going to be capital A t e to the negative t minus 2 capital A e to the negative t minus capital A t e to the negative t is equal to e to the negative t. Again, you can just multiply, well, I'll just do this first. So immediately I see that this and this cancels. Because at e to negative t, at e to negative t, there's a minus. So those cancel. So we're left with just negative 2 a e to the negative t equals e to the negative t. You can, of course, just stare at this and be like, well, a has to be what? It'd be negative half, right? Because you're just like saying, I need this to equal this. So it's just saying like negative 2a has to equal 1. So of course that's going to give you that. So we got it. We have, unlike when we had the original proposed form, had an issue because it immediately gave us a false statement. So we don't get a false statement if you multiply this by t. You'll have a harder time computing derivatives because it's a product rule now. And you plug it in, and we don't get a false statement. So that's good. And you're trying to get this solution form we're trying to force this solution form to satisfy this differential equation. So that's why we're plugging it in and then saying, what must that capital A have been in order for this to satisfy this equation? And we get that it's negative half, which is a constant. And, we're assuming all these coefficients are constants, so we're not getting issues there. So if you were to, hypothetically plug this particular solution, so therefore our particular solution is equal to negative half times t, because this is the solution form we're using now. Just put it in a green box. Negative half times t times e to the negative t. If you hypothetically plug this in to this differential equation, you should get a true statement, because that's what we forced this by plugging in, and finding a, by plugging in and finding a is equal to negative half. We're in that process. We're finding an a that would force this to satisfy this differential equation. So you could check on your own that this will work, and so that's fine. Now the question is, we know there's this one will for sure not work because this gives us no way of finding capital A, and even before finding capital A, you get a full-on false statement. And so this one for sure doesn't work. But you may be like, but why multiply by t? Like why does that work in this case? And you might have felt more comfortable in the polynomial case because the intuition that you reduce by 1 degree and you need to still have a t term that's on the right to also be a t term on the left. So, but this one, I don't think it's clear why multiplying by t was the correct, would have given us the correct thing. You could always say, okay, it worked in the end. So you can say like retroactively that multiplying t worked. So I guess that's the right thing to do. But it doesn't seem like, as comfortable as like I have this intuition that multiplying by t. But we've seen this multiplying by t before. So in first order equations, we had cases where you have sort of a false statement like 0 equals something that's not 0, if you guys remember that. So it was like right here. Remember, like when you had a negative 3x here and a positive 3 here, and those were two coefficients in front of the x and the t that were the same but different signs. And you initially proposed, you just look at the right-hand side and you saw it's capital A e to the 3t. Okay, this is e to the 3t. So you're like, okay, capital A e to the 3t. And this also gave us 0 equals whatever's on the right-hand side. And this was a false statement. And then I said, you need to multiply by t. And then I initially said that let's just see what happens. And then what I did was I went ahead and even justified it by using what did I do? You remember? It's the integrating factor. So I did the integrating factor to be like, well, had you had a k here, positive k, and you had a negative k. So, I built a general linear first order differential equation with an exponential forcing function with a coefficient in front of x and the t being the same number but negatives of each other, and then did the integration factor method, then you get that automatically there is a solution that looks like this, and you can already see by inspection that this was the homogeneous and this would have been the particular, and the particular had a t to it. Okay, and so even back then you might have been like, I don't really understand why this t would somehow magically make this left-hand side have a form that will resemble the right-hand side. And then, but you went with it and it worked and it gave us in this case, a is equal to 8. But then I was able to justify using the integrating factor. Something similar you might want to see for the one we're just doing. But it's going to take me a little longer to get to that. It's going to be a little bit more advanced for us to be able to see. There's like things like variation of parameters and Laplace transforms later in the class that will give you solutions that are consistent with this idea of multiplying by t. So we're just gonna make that connection that this multiplying by t isn't completely new. We've had that issue whenever we ended up plugging in without the original form, got 0 equals something. That was something we saw before, and then the solution back then was also multiplying by t. Now it's still the same. You get 0 equals something that's not, 0. False statement again. The solution is still multiplying by t. Back then, justification was the integrating factor will also give you that. And this time there's some other method because you can't do the integrating factor with second order equations, but there will be a way to also justify, but it won't be like something I can show you right away. But at least it's consistent. So like it's like back then was also this way. So this time it's also the same way. And it's always been multiplied by t. So just notice that and maybe keep that in the back of your mind that, maybe you can wait a little bit longer to see why multiply by t. There's also other stuff that I said that I need to justify, like whenever you had the characteristic equation and you had a repeated root, remember this one, where you had like, this is your characteristic equation, and you ended up getting r is equal to 3, and it was a double root. And so with the homogeneous solution for second order, it's like one of the solutions is c1 times e to one of the roots plus c2 times e to the other root. But if they're the same, it seems redundant to write two of them. And it would be redundant and not good to do that. So you have to say one of them will be e to the 3t, but the other one will be e to the 3t as well with a t. And so that's why this is the punchline for that. But this one I'll justify using reduction of order. And that I can do a little bit earlier, but it won't be until probably like a week or two for me to justify that. So there are little things that, that are still going to sort of be left hanging for the moment. But the punchline is that you would need to multiply by t to fix, basically, it's going to be consistent for every one of these kinds of cases, and we'll multiply by t. For this one, and maybe I should have said this with this example first, is let's find the homogeneous solution. So let's not to get ahead of ourselves. Well, actually, the homogeneous solutions, I'm just going to use the same. So I saved ourselves a little bit of work, because what changed between this equation and this equation was only the right-hand side changed. So you'd expect the homogeneous solution to still be the same, because the homogeneous solution is just from the left-hand side. You just get the same r squared minus 1 and all this. So I'll just copy and paste this homogeneous solution. So from before, we know that the homogeneous solution would be this. And this is where I'm going to make it's probably even more clear that there would have been an issue. This was our particular solution form that we had proposed, right? I'll take off the red X right here. And if you look at this one, we said that e to the negative t we were proposing would be the solution form for that particular solution that would satisfy this differential equation. But immediately there's an issue, because there are two homogeneous solutions to this differential equation, one of which looks like this, c2 e to the negative t. So what does this mean? This means that if you plugged in c2 e to the negative t into this differential equation, it will satisfy the differential equation with a 0 on the right-hand side, because this is a homogeneous solution. Each of these are homogeneous solutions. So either of them, if you plug into the left-hand side, should give you 0, because this is the solution to x double prime minus x equals 0. So there was no hope for this to have satisfied this non-homogeneous equation, right? This is a non-homogeneous equation, it has a non-zero right-hand side. And this, if you plug it in, will give you 0 on the right-hand side. And if you look at this, it's exactly the same form. This is essentially a match between these two right here. So C2 is like arbitrary. A is not arbitrary technically. A is like, okay, we're about to try to find A that will force this thing to satisfy this differential equation. But this second homogeneous solution is saying this for any arbitrary C2 will satisfy this homogeneous equation. So even if we attempt to try the particular capital A that will force this thing to satisfy this non-homogeneous differential equation, there isn't any hope that you will be able to find it, because c2 e to the negative t for any arbitrary c2 is the solution for the homogeneous equation. So it will always satisfy this equation, not this equation. And remember, the particular solution is the solution that satisfies a solution that satisfies the non-homogeneous differential equation. And then you tack on the homogeneous solution on top of that. But this has no hope of satisfying this equation. And that's why we get a 0 here. That's why it's consistent, because you get a 0 here, because it's designed that for this differential equation, any solution of this form for any arbitrary C2 will give you a left-hand side that's equal to 0, because it is the homogeneous solution. And that's why you got this 0 on the left-hand side to begin with. And so even before you try to plug this in and go through all the trouble of plugging it in and getting a false statement, you could have avoided all of that if you just immediately recognize that this appears like one of the homogeneous solutions, and you're like, well, then you're never going to get this to actually satisfy this non-homogeneous solution. So it seems like I always compute the particular solution first and then the homogeneous solution after. That was okay in the past, because you didn't really have to check things from the homogeneous solution that much. But from now on, I'm going to compute the homogeneous solution first, and then check if our initial particular solution form has any potential issues. Basically, if it matches the homogeneous, then it's going to be a problem. And that also is consistent with what we had before. So if you go way back to the case that we just talked about, which was the first order with E forcing function, exponential forcing function, I mentioned here that if you had this particular solution form right here, a e to the 3t, and then you were to, let's say, compute the homogeneous solution. This one was the first order, so you just can say, okay, you have -3 here, so then it's going to be c e to the positive 3t. But if you look at that, C e to the positive 3t, A e to the positive 3t, those also matched. And so there was no hope for this particular solution to satisfy this differential equation because it satisfies the homogeneous solution. And so I kind of mentioned that back then as well. And so here I ended up saying, well, you could tell you could tell ahead of time that this is going to have a problem by just looking at the coefficient in front of the x and the coefficient in front of the t here, and if they're negatives of each other. But you could have just like computed the homogeneous first, and then anytime you computed the homogeneous and you propose a particular solution that resembles the homogeneous, then you could have also done it that way too. So there would that other just computing the homogeneous first and then double checking your particular against it would have also worked back then. For second order, you will have no other really way to preemptively know without computing the homogeneous solution first. So I don't think it's easy to tell by just looking at x double prime minus x that this would have ended up having an issue and you have to multiply by t. You probably have to go through, the characteristic equation and actually compute the homogeneous and notice if there are any terms in the homogeneous that match with that initial particular solution. And so how do you come up with the correct particular solution form is you first look at the right-hand side. That gives you an initial, but it's still an initial particular guess. It's like a kind of like a guess, but it's like your initial proposed solution form. Then you look at your homogeneous solution and then check for any conflicts or matches, and then multiply by t if there is. So that's the process. There's an extra layer now. It's not just looking at the right-hand side. The right-hand side sets you up with your initial form, but it's still like up subject to change. And you might have to compare with the homogeneous solution. And then the solution for this was multiplying by t, which is consistent with what we've seen before, but for this case, still to be justified. And then I'll just scroll back up and mention like, how did this work in this polynomial case? In this polynomial case, you had a naught plus a1t, and there is a term in the particular solution, this a naught term, that did match with one of the homogeneous terms. So, so maybe it would have been better if I did the exponential first, but it is consistent with this too. So again, for this one, you would say, I have a first degree polynomial on the right. So my initial particular solution will be a general first degree polynomial. Subject to change, I'll do the homogeneous solution and see if there's issues. And then I get this solution. And I notice that one of the homogeneous solutions does match with one of the terms in the particular solution. And so I'll probably need to multiply by t. And then you just take the whole thing and multiply by t. And so that's consistent there as well. Let's see if I have, so this one is just basically solving an initial value problem. So what is it? It's the same equation as this. So I'll just write, so here you have, therefore, x of t is equal to this particular solution right here. Plus the homogeneous solution, which is this one. So this is the solution. And then I'll just copy and paste this and then say we just have an initial. So this is like the general solution. But if you want to find the initial conditions, then you're going to have to just like plug these initial conditions in. So basically, you're just going to have x prime of t. You just have to take the derivative of this, which is going to be, because I got to plug in this x prime thing, so we're going to eventually need the derivative. So you'll have to do the product rule. The purple term is going to be this, because the t is going to go away, and then you have e to the negative t. And then what's the derivative of this is just itself. And then this will be minus c2, because you're going to have to do the chain rule. Okay, so there are two initial conditions. There's this one, and there's this one. And you're gonna like just do both of those. So x naught is equal to 1 means that I got to put 1 into x and 0 into all the t. So 0 goes into this t, that kills that. This is gonna be c1. and then this one C2. So that's from the first one. And then the purple one is the derivative condition. And this is why I needed to compute the derivative here, because this has to equal 0. So it's going to be 0 is equal to, and then I plug in 0 into all the t's. So it's going to be negative half times 1, because e raised to 0. And then there's a minus 0 because this right here is just got a t right there. And then it's going to be plus C1 and then minus C2, which means that you get C1 minus C2, and then I'll shove the negative half to the other side, has to equal positive half. And you've got these two conditions, these two equations for two unknowns. So you have these two equations for two unknowns. You have a C1, C2, C1 and C2 you got to find. And it's just solving this system. So in the end, you will get that C1 is equal to, and I'll write it up nicely. It'll be 3/4, and C2 is equal to 1/4. And because I don't have time, I'll just say that you're just solving these two, right? And I'll just put that in there. So again, second order equations, you'll have two arbitrary constants, C1 and C2. So you need two conditions, usually an initial condition on the function, an initial condition on its derivative. And yeah, you need that because it's two arbitrary constants, you need two conditions. So we'll leave it there and then carry on after the weekend.
Thank you.